where is the stress concentration, and again, stress concentration will become very serious locally around where the loading applied. And for example, if this is a needle, I pinch here, then this wall pretty much will have a hole because of a huge force concentrated there. But here, if I use the same load and using this kind of flat face, this is nothing compared to the needle one. Because for this case, the stress concentration is less severe. Okay, so that is this case. For example, here, that is the meaning why we always, in this textbook, we always use solid plate and to distribute the loading uniformly into the material models. Otherwise, if we directly apply the loading, then we would face is a stress concentration. That is the one we don't consider in the fundamental class. Okay, so that is the purpose. We always use a solid plate, and that's the purpose here. A little bit more discussion is this. If the stress concentration occurs, and again, the serious part, the most serious part is around where the loading applied. If we take a point is farther away from the loading applications, then pretty much there the force, the material be deformed is pretty much uniform. We look at this curve, this diagram here, and this is called the Saint-Venant principles. So that meaning if we pick a cross section, here we have three options. We pick the cross section. Here is the farthest away from the loading. This is a little bit closer, and this is the closest. So if we pick the cross section from this material model, if that is far enough away from here, then you can see the distribution of the stress is pretty much uniform. And here, this is called the profile. For example, this point has a little bit larger compared to this point. Okay, but again, that the profile is pretty much uniform through all the points. For this case, you can see the profile become a little bit more concentrated around the center line, where aligned to the loading direction. For this case, you can see that is even severe. For this kind of highly non-uniform distribution of the stress, we call the stress concentration. Stress distribution of the stress concentrated where to the loading applications. That's it. Okay, and again, while we are concerned about the stress concentrations, because for our design, we always require is this. Back to our initial discussions, in all the structures, I said that I cannot teach you exactly for each problem I cannot teach you is where it could be the maximum stress. But from the lessons of the exercise or test, you should be able to accumulate your own experience to justify where could be the maximum stress. So in that case, we want to know is where is the maximum stress. And for this one, if we can find this is lower than or equal to the allowable stress, then this structure is safe. Right? That is the criteria. So again, how to calculate it and how to identify its locations. That's always the two questions. And from here, you pretty much have a little bit more flavored or taste about the two concerns. And for these sections about the stress concentrations, we will learn this one a little bit more, how to calculate it. Okay, so here in our textbook, we use two material models. The material models by themselves will create the situations where the stress concentration occurs. The first one is a uniform plate, and then we simply dig a hole. We cut a hole out of that. And I can tell you the stress concentrations if this plate or this material is under the loading, uniform loading, the stress concentration will occur just around the parameters of where you cut. Always, the stress concentration will occur at where the geometry is discontinuous. That is kind of the rule of thumb. So, for example, we pick a cross section. Again, why we pick this cross section? Because I know, the authors know, on this cross section, we will be able to dig out the maximum stress, this value. The maximum stress is where the stress is concentrated, this value. How do we know? We can do this one by theoretical calculations. We can do this by the finite elements, by the computer simulations. So for the pioneers, we have the knowledge about this one, and now we just tell you, if we take the cross section which passing through the center of the hole, so we expose this cross section, okay, then we can tell the largest stress, sigma maximum is this one. And now for our design, we simply want to calculate what is the magnitude of this. Okay? How to do that one? We use this curve. The maximum value is this. For this example, the maximum value equal to the average stress multiplied with K. K is called the stress concentration factor. Stress concentration factor. That's it. As long as we know this value, then we can calculate this one. And now the issue is, what are the two values? And to apply this formula, that is from the first one, this formula is obtained from experiments. So we have to follow up the protocols of the experiment. In that experiment, the average is calculated by, we simply divide the force by the smallest cross section. Okay, so which means for these examples, the sigma average will be equal to, again, don't ask me why, I simply follow the design, the experimental protocols. P divided by the closest cross section, and closest cross section, that will be equal to how much? Let me say if let me put into 3D. How about that? So this I highlight here. That is the closest. Cross section. For example, if this dimension is t, and I follow up this dimension here, this is d, and the radius equal to r. So that means here, this area in total will be equal to t times d minus 2r. Right? So here is minimum. That is the minimum cross section. So in this formula, we want to calculate maximum equal to K times sigma average. And now the average is by this formula. And again, we have to follow the protocols here. And what is K? The K is this curve obtained from experiment data. Depends on the geometry. These curves are characterized by the R over D, the radius of the hole, divided by the D. What is the definition of the D? D simply is, okay, you know the D here. The D simply is the summation of this one. Okay. So as long as we know our size, our dimensions of the samples, we should be able to identify this ratio. Once we have this ratio, then we, for example, we can simply identify corresponding. For example, if the ratio is equal to 0.2, then we can identify the corresponding K will be about 2.5. Okay, using this estimation, you will plug in K equal to 2.5 to here. So this one is from curve. Then we can calculate, we can estimate the maximum stress.
Why does that formula give you the average?
Yes.
The average stress.
Yeah,
it seems
because
that if you had a force over the smallest area, it would be
yeah.
the maximum.
Yeah, because here we simply is, if we want to use this formula, we simply use this one, because when they create this formula for the, okay, on one side the maximum, this one can be experimentally obtained or simulated obtained, this value. And we know this value in advance. So the people try to come up with some simple formula to help us estimate this value. And that is this one. And why that formula must taking up the divided by minimum, I don't know. They just somehow they come up with this formula. We just take it. Okay, we just take it. And again, here I want to emphasize this is the minimum cross section, which means just here and here. If for many times the people try to take this cross sections in the calculation in the homework or in the test, which will lead to you the different numbers, which is incorrect. This is the only place I will ask people to memorize. 99% of the engineering stuff shouldn't be memorized. That should be deduced logically. But this is a few exceptions. I'm sorry, because that's the standard, and we have to follow up. Okay. So that's your question?
Yeah.
The second example, the material model, is we have fillet. So that means we try to curve the angle here. If the angle here is not curved, then I can tell you the stress. For example, here is if we have the material models just like this, and that is perfectly 90 degrees here. So this is our material. Okay, if this material is under the axial loading, then here is very likely, you can tell it is very likely to break, to get a fracture there. Okay, so that reason here we try not to prevent, so basically we make a curve. But this curve still have a little bit more, still have the stress concentration. So here, if we pick the cross section, that is just at the end of the curving. So that's the cross section we pick here. Then that value is our maximum stress. And again, we have a similar formulas. The maximum for this case, again, the maximum equal to K times the average. Again, what is the average? The average is the force divided by this area. Let me put it into 3D. Okay, that is the area. And for this case, the area, for example, let me call this is T, thickness T, and that dimension is D here. So area equal to TD. So therefore, the sigma average will be equal to P divided by TD for this material model. And again, for this material model, we to uniquely identify the K, we have follow up this curve. Here we have the ratio R over D, and we have to also calculate the ratio between the capital D to D. We simply follow those informations. So probably today I don't have time to finish one or two examples. But I think these examples are pretty much straightforward for you to follow up. So would you mind just do the self-study on this one here? And in one of the homework problems, one final note, I want to remind you, in one form of questions, we have materials like this. We have fillet, and also we have a hole. In this material, we have a combination of the two things. So for this example, you simply decompose these conditions into the two standard models, and you calculate the corresponding maximum, and then whatever the design, then you simply pick all the maximum and to compare to the design criteria for the justification. Again, for this model, you simply decompose into the two standards and work individually. Okay, great. Thank you.